So I managed to cobble together another Substack article. I really like the premise behind it, but I've had a hard time communicating or even thinking about it. The title of the article is "The Universe is Collapsing," and then in parentheses, "at all points." Now in the article, I'm not arguing that the universe is collapsing, at least not in the traditional sense of the word collapse. The premise I'm trying to communicate is that there is no such thing as a global solution, a global metric solution to the Einstein field equations. That's the point of this video and of that Substack article. So let's get into it and see if I can describe this in a coherent manner. This is my favorite Far Side comic of all time. I love this thing. I remember this. One of the reasons it's my favorite, I mean, it's a great concept. It's funny. It's humorous. But also, one of the reasons is that it's very rememberable. I don't know why. I'm terrible at remembering things, but every time I find a Norman door, I think of this Far Side post. A Norman door is typically a door, but it could be anything that is poorly designed. It's named after Don Norman, who wrote a book titled The Design of Everyday Things. Norman doors are everywhere. It's because when people are building or designing something, they tend to cut corners as much as possible, and thinking about things is one of them easy to do, or easy things not to do. According to Don Norman, good design has two features: discoverability and feedback. When you look at the object, its design should be the instruction manual. That's what he means by discoverability. You should be able to look at it and know what to do with it. And then the feedback part is that when you interact with the object, it should actually tell you what it's doing. It should give you that click, that ding, whatever it is that tells you you're doing the right thing or the wrong thing. Theoretical physics could learn a lot from Don Norman. There are tons of Norman doors in physics. The Big Bang Theory is just one big giant Norman door. The FLRW metric, which is the metric solution used in the Big Bang Theory, is the perfect example of a Norman door. If you look up the definition of cosmology, you'll likely find that it's something like the study of the evolution of the universe, or something similar. But the entire field is a misinterpretation of general relativity and predicated on the expansion of the universe. There is no global evolution of the universe. There is no global expansion. The universe is this process. It's like a collection of matter and energy that's governed by certain rules. And those rules don't change over time. The spirit of the cosmological principle is that no observer should find themselves in a special part of the universe. It's a statistical argument predicated on the largest scales. I think that we should extend the cosmological principle to include time for exactly the same reasons. In other words, if time is infinite, we shouldn't find ourselves to be in some privileged era of time. General relativity is a theory about relationships. It's a remarkably accurate theory with an enormously successful track record. But virtually 100% of the metric solutions created by all these big-brained academics, they're just simple approximations. No matter how good they are, it's still just an approximation. This is not what we're looking for in physics. I mean, it is, but it isn't. Ultimately, we want to know the exact equations and formulas of all the physical laws in the universe. Approximations and assumptions and symmetries, these are helpful to get us there. But ultimately, we want the exact definitions. Now, the nature of general relativity invites a lot of these approximations, and that's because the equations are incredibly complicated. In order to make them solvable and tractable, you have to come up with an ensemble, or whatever symmetry a theorist can come up with. You do the best you can to be able to balance the field equations. There is no official taxonomic system for all of these various metric solutions, but typically the solutions are broken down into vacuum versus non-vacuum, or global versus local, sometimes by symmetry group, physical interpretations such as a black hole or a galaxy or whatever. But in reality, all of these metric solutions are just approximations. Take the FLRW, for instance. The FLRW assumes the universe is expanding, as well as being homogeneous and isotropic on the largest scales. So this structure was chosen because it makes the solutions tractable, and it's what physicists have from the observational data. That's their interpretation of what's going on. But it's not really accurate if you sit down and think about it. Isotropy means the type of structure in all directions. And I'm fine with using the term isotropy because it's essentially like claiming the universe is symmetrical as you zoom out. It gets more symmetrical as you zoom out. And that every observer can pick up a telescope and look through and see galaxies, clusters, things like that. So that's fine. Isotropy is fine. But homogeneity, on the other hand, that right there is a pull handle on a push door. Mass density is a scale-dependent variable. So it's literally impossible for the universe to be homogeneous. No matter how much you zoom out, mass density is still going to decrease. There is no point at which you reach some magical large scale and the mass density smooths out and becomes stable. This is a fantasy. Mass density will always go down the further you zoom out. So homogeneity is the wrong word to use. But this is why it's difficult to come up with any type of global metric solution. I mean, you always want to describe reality the best you can, but it's not straightforward on how to do that. Not to toot my own horn here, but the metric that I have constructed is by far superior to the FLRW in every possible way. My metric is constructed by decoding cosmological data. It's a static, spherically symmetric, non-vacuum, asymptotically non-flat, observational metric with a linear potential and a horizon. The profile, the horizon, the CMB temperature, the BAO preferred scale, flat and rising curves in galaxies, dark energy, and a lower and upper bounds to gravity and energy are all derived from a single observable, the Hubble redshift. This is virtually bulletproof and gold-plated as far as physics goes. I don't know of anything like it. But even my metric is not a global metric. And that's the point of this video, that there is no such thing as a global metric. Really it's that cosmology is a field that should not exist. It should just be called general relativity. So the universe is assumed to be infinite in all directions. It's entirely likely that our observable universe is some tiny microscopic patch in an infinite sea of other observable universes, okay? So just the most unimaginable size you can think of. Now, some parts could be expanding and some parts could be collapsing. But this is not the same type of expansion and collapse as proposed by mainstream cosmology. When cosmologists say the universe is expanding, they're referring to something extra, some additional phenomenon outside of general relativity. They're not claiming the universe is expanding because of the distribution of mass. They're claiming that spacetime expands. Now, this type of global solution works outside of general relativity, but it uses the tools of general relativity. In many ways, lambda cosmology is treated as superior to general relativity. Now, of course, that's nonsense, but space, time, the definition of density, the laws of thermodynamics, these are all warped to accommodate the Big Bang Theory. Global solutions should be congruent with all laws of physics, but they must absolutely work within the rules of general relativity. At the very least, I don't even think global solutions should exist, but at the very least, they should work within the rules of general relativity. Now, lambda cosmology is allowed to sidestep these rules, all in the name of something else, some new mysterious phenomenon. And it ends up being more powerful than anything known to man. But there isn't even a need for a cosmological solution anyways. General relativity is the global solution. It is the cosmological solution. It is our cosmology. That's the point of it. General relativity describes the universe as a relational framework. A metric solution is just a method of using that framework to dissect the data and make predictions. No one ever talked about creating a global solution for Newtonian physics. So I'm not sure exactly why general relativity is different. Einstein's original static universe was said to collapse if you didn't use a cosmological constant. But the interesting thing here is that collapse means it collapses to all points in space, not some specific place, but to all points. And so this is essentially the same as claiming that gravity is attractive. Like there's no difference here. This is what objects do collapse. Things go towards other things. But claiming the universe would do anything like collapse or expands globally, well, this is nonsensical. Collapse and expand are things that objects in the universe do, not what the entire universe does. Of course, mass is attractive, but there's an infinite sea of objects to fight over what piece gets gobbled up. There's also an upper and a lower bounds to gravity's reach and the amount of energy that you can pack into a region. So it's not going to collapse. It's just that gravity is attractive. That's what general relativity tries to tell us. And there's no need for a global solution, but you have to come up with solutions to be able to make predictions. But those solutions are scaled. It depends on whatever you're talking about. If you're talking about the solar system, you have a solution for that. If you're talking about the galaxy, you have a solution for that. A cluster of galaxies, you have a solution for that. Anyways, I think I've made my point. This is long enough. What are we at? 15 minutes? That's fine. Thanks for watching. Give me a like, subscribe. Oh, buy the book. There's links in the description below. So buy the book and give me a good review. Yeah, do all those wonderful things for me. I'm not a YouTuber. I just like this stuff, and I don't think a lot of people have put much thought into general relativity and cosmology. This stuff is very abstract, and you got to really sit and think about it a lot. Anyways, y'all have a great day.